In this video, I'm going to solve this related rate problem. So I'm given that an airplane is flying at a constant rate of 500 miles per hour and as well a constant altitude of 3 miles, and it passes directly over an observer. And I want to figure out how fast the plane's distance from the observer is increasing at a particular time. So the first thing I like to do is I like to think about what I'm given and assign my variables. So this is a good situation for drawing a picture. All right, so I've drawn the picture. So we have an observer down here, and we're given that we have an airplane flying, and it is 3 miles. It's an altitude of 3 miles. So that is actually a fixed distance. So that is 3. We should use that in our problem. It's not changing in this problem. Now we're given that the plane is flying at a constant rate of 500 miles per hour. That means that this distance is increasing at a rate of 500 miles per hour. So let's give it a label. So we are given that dx by dt is 500 miles per hour. And we also want to know how fast the plane's distance from the observer is increasing at a particular time. That is this distance, right? That's the plane's distance from the observer. So we should label that distance as y. And that is a distance that is changing. And so let's think now about what it is that we want. So we want to know how fast the plane's distance from the observer is increasing when the plane is 4 miles from the observer. So that tells me that we want dy by dt when y is 4, right? That would be when this distance is 4. Now, that's not always 4, right? So we can't just plug that in at the beginning. We're going to use it at the end when we're trying to figure out dy by dt, because at that point, that's when we know that we want that changing rate exactly when y is 4. So the next thing we should do is we should relate our variables. So let's relate. And a good candidate for a theorem to use to relate these variables is the Pythagorean theorem, because I've got a right-angled triangle. So let's go ahead and do that. And so if I do that, I have x squared plus 3 squared, which is 9, is equal to y squared. So the next thing I want to do is differentiate. And we're differentiating implicitly with respect to time. So we get 2x dx by dt. Derivative of 9 is 0. And that's equal to 2y dy by dt. And now I like to think about what it is that I need. What do I need? So I do a little checklist here. So I'm given dx by dt. I want dy by dt. I'm given y. I am missing x. So I need x. Okay, so how can we figure out x? Well, we'll go ahead and use the Pythagorean theorem. And we want x when y is 4. So that's something to keep in mind. So we want x when y is 4. Okay, so using our picture, we have x squared plus 9 is y squared, which is 16. So x squared is equal to 16 minus 9, which is 7. Technically speaking, x would be plus or minus the root of 7, but of course x is a distance, so it's positive. So we have x is the square root of 7. And now we have everything we need to solve this problem. So let's go ahead and substitute and solve. All right, so using our relationship right here, we have 2 times x, so 2 times the root of 7 times dx by dt, so that was up above, so that was 500, is equal to 2 times y, and we can now use that 4, and we have dy by dt. So that tells me that dy by dt is 2 times the root of 7 times 500 over 2 times 4. Simplifying that, that becomes 125, and I get 125 times the root of 7. Now let's go back and remind ourselves of what it was that we were trying to find, what our units are, etc. So we wanted to know how fast the plane's distance from the observer is increasing, and we're working in miles per hour. So we've got that, and so now we can just close off this problem. So the plane's distance from the observer is increasing at a rate of 125 root 7 miles per hour.